Section 10.3, Taylor's theorem. I've included our examples from the previous classes. Example 1, so at any time, when you go look at the video, the solution will be here, even though it's not in real time. You can pause it and go back and look. So there's our example 1. Example 2 that we did last class. Here is where we left off yesterday, where we talked about the fact that our remainder, or our error, will be equal to our n plus first term, the first omitted term. And actually, I want to start here. All right, so we will be using what is called the remainder estimation theorem, also called the Lagrange error bound. You should know that name as well, because sometimes you are asked to use the Lagrange error bound to find the maximum possible error in your approximation. Remember, we are using a truncated series, so we're using some polynomial to some degree to approximate some function. And when we do that, we always introduce error, and we need to have some idea of how big our error is. So that's what we will be finding. Now in your book, it gives the Lagrange error bound. I don't know why this came out so small, but I can do something about that. We'll make it a little bit bigger. There we go. Okay, so in your book, they give the Lagrange error bound as it appears here in the box. And they refer to that n plus first derivative. They replace it with m times r to the n plus 1. Now, all that is a way to find the maximum value of the n plus first derivative between a and x. So, I prefer that we use this version of the Lagrange error bound right here. So this is what I would like you to have in your notes. The absolute value of r sub n is less than or equal to the absolute value of the n plus first derivative at c. Please note that that is not at a, and it is not at x, times x minus a to the n plus 1 over n plus 1 factorial. You need to have that in your notes. That is our Lagrange error bound that we'll be using. Again, it's the first omitted term, allowing us to find out how far off our approximation is. That's an A. That was an A. Now it's an A. All right, so we need to clarify and deconstruct the parts of this error bound. So the first thing we see is this f raised to the, in parentheses, n plus 1 of c. We remember when we see the n plus 1 in parentheses, it's a derivative. So what we're talking about here is if we have a polynomial to the 5th degree, then I will be using the 6th derivative to calculate my error. Okay? And this is the n plus first derivative in the interval, and we want to find the biggest possible value of this in the interval because we want to find the maximum error. We know that this n plus 1 factorial is going to end up dividing by a larger number, so by finding the largest value we can here for our n plus first derivative, that will help us maximize the possible error. Okay. All right, so that is the n plus first derivative at c. Now this value of c is going to be some value between a and x where the maximum derivative occurs. All right, remember a is where our series is centered. where we shifted it. X is the value that we're interested in. All right, so we may have a series that is centered around 1, but we're interested in f of 1.2. So that 1.2 would be our x value. And c is going to be somewhere in that interval, and it has to be the place that makes the derivative the highest. Okay, and then we have a is the value around which the, it says the x value around which we are centered. And then our n, well, if we have a 6-degree polynomial, that's a 6, then our n would equal what? 6. And then our n plus 1 for everything we need in our error bound would be 7. Okay, so once we have all of those things defined, let's go find out how we can use this to calculate error.
Can you go back?
Oh, can you? Yeah. The value around which we are centered. Sorry, I had to screencast it. We good? Everybody good? All right, we're moving on. Connor, you with me?
Yeah.
Andrew, you with me? Okay, good, excellent. All right. Now, the difficult part, or the most difficult part of using this error bound is finding where the maximum of that n plus first derivative occurs. So when let's say we have a polynomial of 6 degree, we're going to need to find the function for the 7th derivative, and then find where that is the biggest in our interval. Well, when we get our 7th derivative function, if that function is strictly decreasing, then where does the maximum occur? At a, at the left end of our interval. If the 7th derivative were strictly increasing in our interval, then the largest would happen at the right end, or at our x value. It becomes a little more difficult when we are increasing and decreasing in the interval, and they have to give us some other way to find that c value where the maximum occurs. Sometimes they give a graph, sometimes they give some background information in the directions of the problem, but there has to be some other way to find our maximum derivative. So when you find your n plus first derivative, you need to think about the function. Is it decreasing only in the interval? Is it increasing only in the interval? Or where can that maximum occur? Okay? All right. This is the example from your book. I have it completely worked out, and I'm not going to step through it right now. I just want to show it. So again, you can look at it and pause it when you watch the video. And it gives a little more information than given in the book in solving this problem. So please come back and take a look at it. But I would like to start with, let me go back. This is number 9 from last night's homework worked out. That might be helpful when you're looking at the homework again tonight. All right, the example I want to look at is this one. Use a 5th degree Maclaurin polynomial to approximate e to the 0.7, then find the Lagrange remainder. So the first part, I'll call part A, a 5th degree Maclaurin to approximate e to the 0.7. All right, well, what's the Maclaurin series for e to the x? It's 1 plus x. There we go, plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial, plus x to the 5th over 5 factorial. Why do I go out to the 5th? Because it told me to go out to the 5th degree. So that's as far as I need to go. So if I want e to the 0.7, what do? Replace the x's with 0.7. 1 plus 0.7 plus 0.7 squared over 2 factorial plus 0.7 cubed over 3 factorial plus 0.7 to the 4th over 4 factorial plus 0.7 to the 5th over 5 factorial. And I think we end up with 2.3017. I think that's what we get. All right, so there we've done the first part of the problem. It says then find the Lagrange remainder. What do I write for a Lagrange remainder? Absolute value of r sub n is less than or equal to the absolute value of the n plus first derivative at c times x minus a to the n plus 1 all over n plus 1 factorial. So now let's deconstruct this like we did before. What is our n? 5. It is the degree of our polynomial, which means n plus 1, which we'll be plugging in, is 6. What is a?
0.
A is 0. Our function up here is not shifted to the left or right, it's just x minus 0. So our a is 0. What is our x value? Our point of interest? 0.7. All right, I have just about everything. The only thing I don't know is c and the 6th derivative at c. So now we want to go and figure these out. I'm going back. I just had to get rid of it. Okay. If I need the 6th derivative, then I need to know what f of x is. What is f of x? E to the x. That's the function we are using. And that's very nice, because what's the 6th derivative of e to the x? We love that one. You will find quite often when you do Lagrange, they like to toss in e to the x for this purpose, because many other derivatives get very difficult as you continue. Yes?
Jesus use 0 for a.
No. Looking at our series up at the top, we use the e to the x series, which is centered at 0. So each of these is x minus 0 to the first, x minus 0 to the second. There's no x minus 2 or x minus 1. So the a value, the shift, is 0. Okay, so you get it from the actual series. All right, so that's nice. And now we need to think about if our 6th derivative is e to the x, and our interval is from a to x, that's from 0 to 0.7. E to the x is exponential growth, correct? Tell me about that function. Strictly increasing, so where is the maximum of our 6th derivative happening? At 0.7. So the max of the 6th derivative will happen at 0.7. And what is that? E to the 0.7. So now we can fill in everything. We're finding the remainder after a degree of 5. It's less than or equal to the absolute value of e to the 0.7 times what? 0.7 to the what power? 6 all over 6. 6 factorial. There we go. And there is our maximum error for our polynomial that we wrote up in part A. Does anybody have a value for that for me? If you had no calculator, you would leave it in this form. Or you could say e to the 0.7, well, that's pretty close to e to the first, right? So you could just leave this as e and state that you're making that approximation if you have no calculator. Or you can leave it just like this. Does anyone have a value? 3.2, what, 9? Times 10 to the negative 4?
Yeah.
Good. All right, so what does that mean? Well, that means my approximation up here of e to the 0.7 being 2.3017 is less than 3.29 times 10 to the negative 4 off of the actual value. Okay? That is the maximum error in this interval.
greater?
No. It can't be bigger than 3.29 times 10 to the negative 4, because we found the biggest value of the derivative in that interval. So that means,
I'm sorry, I meant like maybe like off either way.
oh, yes, yes, plus or minus, absolutely. Because this is an absolute value, so it can be plus or minus. The error will be within the range of plus or minus 3.29 times 10 to the negative 4. That's a good question.
Would that be your full answer?
Yes, this is the maximum error right here. Okay? All right. How am I doing on time? Oh, I never get to this next one. It's my favorite example. All right. I won't even start because I'm going to run out of time. I'm going to pause this. Okay, so our last example gives us a table of values, so let's read through it. Selected values of f and its first 4 derivatives are indicated in the table below. The function f and its derivatives are decreasing in the interval 0 to 4. So they're basically telling us that the derivatives are decreasing. Which most likely will tell us that our n plus first derivative at c, what does it tell us if they tell us the derivatives are decreasing? In my interval, right, at a to x, we're going to let c equal the left end for a, because we've got something like this. So our maximum value of the n plus first derivative will be at a. That's just something to keep in mind when we get there. So the first part says, write the third degree Taylor polynomial for f about x equals 3 and use it to approximate f of 3.1. All right. So if I need to make a Taylor polynomial about x equals 3, then what I'm looking at is f of what? When I write out my series, it'll be f of 3 in this case, correct? Plus f prime of 3, x minus 3, plus f double prime of 3 times x minus 3 squared over 2 factorial, and then it would continue on like that. Yes? This is our shifted Taylor polynomial. Okay, well, question? Oh, you're right, I should go one more. We will go one more when I actually make it, so I'll add that in. Third degree, the third derivative times x minus 3 cubed over 3 factorial. So for the polynomial we're looking for, that's as far as we would go. So the nice thing is, they've given us all this information in the table. What is f of 3? 12 plus f prime of 3, so I should say minus 31 times x minus 3, then minus 48 times x minus 3 squared over 2 factorial plus, nope, minus what? 81 times x minus 3 to the third over 3 factorial. So get your calculators out, please. And we're going to use that to evaluate f of 3.1.
Got 8.6465.
8 point what?
6465.
6465. Okay? And all we're doing there is putting in 3.1 for each of our x's and calculating. Any questions on what we did with these? Okay, so that's nice and straightforward. Let's move on to the second part. And, yes, I want these here. Use the Lagrange error bound to show that the third degree Taylor polynomial, or f, at x equals 3, approximates f of 3.1 with error less than 7 times 10 to the negative 5. So, the way we can do that is by finding the maximum possible error by using the Lagrange error bound. All right, so let's figure out all of our parts of our Lagrange error bound. What is our n? It is 3. So our n plus 1 is 4. What is our x? 3.1. What is our a? Not 0 this time. Think back to our series. It's 3, yeah. All right, our c we don't know yet. We can think about. We've discussed it a little bit, but we'll get there. And we'll need our, which derivative? The n plus first derivative would be the what derivative? F parenthesis what? 4 at c. Okay. So they told us that our function is decreasing, so we want to use the left end in our interval. Well, our interval is from a to x, which is 3 to 3.1. So which do we use? We use 3. We're decreasing. So we let c equal 3. And that's very convenient considering the table we were given, which I'll refer to in just a minute. So let's go ahead and start filling in our Lagrange error bound. We're finding the absolute value of our remainder, so 3, is going to be less than or equal to, oops, please make sure that you change this to a less than or equal to up here. That shouldn't be equal. The absolute value of the fourth derivative at 3. Well, we had a table that's just given to us.
If c wasn't 3, we get to plug it into whatever.
Right. So they would have had to give us a function to take the derivative, which they didn't do for us here. So this is what I mean. They sometimes find a way to give you the information in some other form. So they told us the fourth derivative at 3 was negative 16. So now we go back, and what will I have here? It'll be negative 16, but it's going to end up getting an absolute value on it, so that negative is going to go away in the end. So let's just leave it there for now. And x minus a, 3.1 minus 3 to the fourth, all over 4 factorial. Times 0.1 to the fourth over 4 factorial. Get rid of my absolute value because I've taken it. And what do we get? Less than or equal to?
6.667 to the negative 5.
So that's,
Sorry, times 10 to the negative 5.
that's same thing. I'm with you. Right. I wrote it the way you said it, but I pictured it the way it was on the calculator. Times 10 to the negative 5. All right. Well, let's remember what we're trying to show here. It says, use the Lagrange error bound to show that the third degree Taylor polynomial, or f about x equals 3, approximates f of 3.1 with error less than 7 times 10 to the negative 5. Did we show that? Yes, because our error was 6.67667 times 10 to the negative 5. So we'll finish by stating the solution is less than 7 times 10 to the negative 5. So we have answered the question that they gave us. Okay? So the tricky part is figuring out C and the fourth derivative of C, and it's different in every problem. We can switch up, we have to think about it each time about how we're going to solve that. All right, I'm going to go back and look at example 5 out of the book so we can step through the solution. We're estimating a remainder. It says the approximation of the natural log of 1 plus x is approximately equal to x minus x squared over 2, and this is used when x is small. Use the Lagrange form of the remainder to get a bound for the maximum error when the absolute value of x is less than or equal to 0.1, which means x is between 0.1 and negative 0.1. All right, so if we're using the Lagrange form to find our error, we write down our Lagrange form over here, and we start figuring out all of our parts. So our n is what? What's our degree of our polynomial? It is 2, so n is 2. Our a, is there any shift on this? Do we have x minus anything or x plus anything in our original? We do not, so our a is 0. Our x that we're interested in is 0.1 because absolute value of x has to be less than or equal to 0.1. So we're just choosing a value in this region. Most of the problems will be more specific about your value of x. This one is a little unclear, but we're going to choose the right end of our interval to work with. And so our n plus 1 is 3. All right, so that means I need the third derivative for my f n plus 1 derivative of c. So over here on the left, I have my function. I have the first derivative, second derivative, third derivative.
So is that how you got your C?
That's how I got my c. So looking at my third derivative, it's 2 over 1 plus x cubed. If I look at that graph in the interval that we're interested in, negative 0.1 to 0.1, it is strictly decreasing. So if I want the maximum, what do I use? The left end. We let c equal the left end, or c, I should say, decreasing, so max is at x equals negative 0.1. Exactly. I'll write that right up there.
But x is going to be equal to 1.
X, yep, we'll still use 0.1 on this. All right, now let's plug in and see what we've got. So I evaluated my third derivative at negative 0.1 and got 2.743. Yes,
Do you always take the absolute value of the derivative?
yes. We want an absolute value here, we want a positive value here, not a negative.
So if there was a negative on it, would you first take absolute value and then evaluate it with the
With a positive.
positive
Yes.
value?
All right, and our maximum is happening in this case. So I had x equals 0.1. In this case, it won't matter because we're taking the absolute value. So really, for negative 0.1 for our x, since we're using our maximum at negative 0.1, I chose to put that in here for my x minus a cubed. And we take the absolute value, it's still 0.1, cubed over 3 factorial. So our remainder ends up being r sub 2 is less than or equal to 4.57 times 10 to the negative 4.
Which is less than 1.
Nope, we're just trying to find the maximum error when we're